Hi everyone, welcome to lesson 4, model validation. So model validation is checking to see how well your model is working. So we train it, we give it some data, we give it the answers and the features, and then it starts trying to fit the model and make the regressor tree work in a way that does a good job of taking the inputs and giving us correct outputs. And that's great. So it goes through, it does all that. But then the question is, well, how good is it on predicting other house prices or other data in the world? And that's what's called model validation. That tells us how far off our model is from reality. To do this, we've got a couple options. One that we did so let's talk about this real quick. What if our model was doing things like this, where it was predicting house prices that are off by, say, $100,000, but sometimes the $100,000, it was too high on what it thought the house price was, and other times it was $100,000 too low on the house price. And we might think to ourselves, oh, well, if it's too high sometimes, too low sometimes, on average, it should be pretty good. It should be right on, in fact, and on average. The problem with that, though, is that if you use our model, say you're trying to sell your house and you type in your address and your bedrooms and all that kind of stuff, and you send that information through the model and it tells you that your house is worth some amount, and that amount is $100,000 too much, you're going to list your house for that amount and then never be able to sell it because everybody's like, that's too expensive. So that's a problem in of itself. So if we give back answers that are $100,000 too much, that's going to be a problem. Or you're buying a house and you use the model to try to say, how much is this house really worth? You might think the house is worth more than what it really is and end up paying more than what you should have to buy the house. So that's a problem. Then what if the model returns a value that's $100,000 too low? So in that case, if you're selling your house, you might actually sell your house at a price that's less than what you should have sold it for. So you'll lose money there. That's going to super annoy you. And if you're a buyer and you go to look at a house to buy and the model is $100,000 too low because of error, you're going to think that house isn't worth it, and you might end up passing on a house that you could have purchased, would have been happy to purchase at a different price. So the model needs to be right on for each house. There is no averaging out. A high error doesn't cancel out a low error. They just cause different problems. So if we just take the amount of error, so how we would do that, we would take the actual price that we know is the real price, we'd subtract it from the predicted price, and we would get either a positive or negative difference there. So how far off it is from that. And in reality, we don't care if the price is too high or too low. We just care that it's wrong and by how much. So the way to get around that mathematically is to use something that's called the absolute value. And all the absolute value does is says, hey, we don't care if something's too high or too low. We just care how far off it is. So if the number is negative, it just makes all negative numbers positive and leaves positive numbers alone. And once we do that, we can take the average, and now we'll have the average for how far off it is. I gave the example before of 100,000. If 100,000 over is positive 100,000 error, and $100,000 under the correct value is a negative 100,000 error, normal averages would be 100,000 plus negative 100,000, which is 0, divided by 2, which is $0 of error. And that's really confusing because it was really wrong in both houses, just in different directions. That doesn't feel like the correct way to do error for the model. Whereas if we do the mean, it's called here the mean absolute error. First, you find the amount of error in there. So positive $100,000 too much. Negative 100,000 would be too little or too small a number. You take the absolute value of both those numbers. So the 100,000 is 100,000. The negative 100,000 turns to positive 100,000. Then you find the average of that error. So 100,000 plus 100,000 would be 200,000. Divided by 2 would be $100,000 of error in our data. And that way when we report our model, we're saying, hey, we've got this great model we just got, but it has $100,000 of error in it. People know to be cautious with the values. All right, so that was a quick discussion of mean absolute error. And the reason we use the absolute value is because high error doesn't cancel out low error. That doesn't make any sense in our model. If it did make sense that those canceled out, we might be able to not use absolute value. But when those don't cancel out, like in this case, we've got to use the absolute value there. All right, hopefully that helped. And then here is the actual minus predicted. And then you would take the absolute value of that and then take the average of all of those. And so here's that code for it. Now we know the import pandas we've done several times. Now let me see if I can zoom in a little bit. Import pandas is PD. So pandas is this data handling library that does all the kind of reading our values and things. We create a file path for where our file is being stored. And then we do a PD for the pandas library, read CSV. We read in this file path, so this melbdata.csv. We convert it from a CSV file, being done here by the read CSV, into what's called a data frame, which is a data table for machine learning. I apologize. This is a step we don't do in our assignment because our assignment doesn't have missing data, but this searches this Melbourne data.dropNA. The dropNA, what it does, it searches the Melbourne data frame. Any rows of data, so any houses that are missing any piece of data in them, it just deletes that row of data so we don't get a mess up of having an empty column. We can't have empty cells going through our model or it won't work. So that's this, and then we store that when we go through and we drop all those rows out, and we store the new data frame in something called a filtered Melbourne data. They just changed the name so we could have that sort of smaller data table here. And then we said, hey, we want to use price as the predicted values, and those are stored in a series called Y, so like a list. So we say, go to the filtered Melbourne data, that new little data set we have, grab the price column, pull that price column out, and put it in this, this list called Y. So now Y contains all of the prices in order of all the different houses in the filtered Melbourne data list, or data frame, I should say. Now the next thing we need to do is we need to pull out all of the features that we're going to use to do the predictions with. So we make a list of all of the different columns in this filtered Melbourne data frame that we're going to use to make predictions with. We're going to use rooms, bathroom, land size, building area. All of these are going to be used to make predictions with. So we created a list of all of those. And then we came down here and we said, okay, we're going to take the filtered Melbourne data. We're going to we're going to tell it, go get all of these features, all of these columns from that data table, and put them into a new data frame called X, capital X. And that's the convention, just the agreement that everybody has when they're doing machine learning, that the stuff going in as the features, we're going to call capital X, and the things that we're predicting, we're going to call Y. All right, and we've done all of that before. And then here, we're going to go to the sklearn.tree, and this is where we're going to go get our the tree that we're going to use, the decision tree we're going to use for actually doing the model with. So we're going to import the decision tree regressor model. Now when we import this model, it's completely untrained and unfit. It's just like kind of a blank outline of what's going to happen. Then we need to actually create something to store the model in. So we create a Melbourne model, a variable like this, and we say get a decision tree regressor. And in here, we really should give it a random state. So random state equals 1 to give it a starting state so that every time we run it, it gives us the same answer every time. They just forgot to in this code, but it's a good idea to do that. The only bad thing about if you do it like this and you don't do that is every time you rerun this code, you'll get slightly different model coming out and slightly different predictions. They won't be off by much, but a little bit, and it might be confusing why it's always a little different. That's just because it's starting with a different random state when it first starts. Next thing we need to do is, so we've created our model, we've defined it. Again, we haven't adjusted it yet. We're going to come here now, we're going to go Melbourne model fit X, Y. So when we fit, we tell it what were the features that we're going to use for predictors, and then what we're going to predict here. So what it can do is start with those X's, and it can evaluate how well it's doing at predicting the Y's that we already know. And it can run this fit over and over again, constantly looking for ways to make this work better and better and better. All right. And then now now that we have our model fit, we've adjusted it and it's all ready to go. We think it's predicting really well. we need to go ahead and start doing some predictions for it and test it to do some validation. So here we do sklearn.metrics import, and we're going to import the mean absolute error. And all this does, this is just kind of a lazy way. We don't want to create all the code for going through and checking all the mean errors. It's already been built in for us, so we're going to just go grab it from the sklearn.metrics library, and we're going to grab the mean absolute error calculator. So it's going to make our life easier later. So now what we're going to do is come over here. We created a new variable. We'll talk about what that is in just a second. We're going to go to our Melbourne model, and we're going to do dot predicts x. So we just trained it with all of our x data, and now we're going to run our x data back through and see how it does actually predicting the value of those houses over again, and see how well it does. And we're going to test it by saying mean absolute error y comma predicted home prices, and the output of that, and what this is finding the absolute error between the actual y's and then the predicted home prices we got from running the x's through again. So these two lists are the same number of items. I've got a ton of houses in there. Just going to go through and calculate it. And lo and behold, our mean absolute error was only $434. So this number means that our values are only $434 off of what the actual values are, which is absolutely amazing to get that good of results. In fact, when we did this in lesson 3 in the video, we actually saw that the first 3 and the last 3 of the houses in the list, they were all actually perfect. There was no error in them at all, which kind of explains why some of them are off a little bit, but it's only $434 off. So that's pretty cool that we got such good data. The problem is, though, this is big time cheating. So what we've done is we've trained the model on this set of data that it knew the answers to, and it fit the model and adjusted the model so that it would give good answers that it knew already. And then we gave it back those same houses and said, now try it. But it's already created the model specifically for those houses, so no doubt it's going to flow through really well because it did that purposefully for those houses. And the question isn't how well can it redo the houses it's done. It's like playing Jeopardy the second night you've seen it. It's a lot easier than the first night you've seen it because you kind of remember the answers. This is your model kind of remembering the answers. So it can just kind of flow through and get almost all the houses in the exact right places. So it's gonna appear super accurate. So what we want to do is we want to actually always test our model with data it's never seen before. So we need a chunk of houses that the model hasn't been trained on, it's never seen before, and that we know the prices of, so that we can run those through the model and see what it predicts and then compare to what the actual prices are. That's going to be a fair comparison. And this is just a discussion of the problem with in-sample scores, is a discussion of that problem, of this idea that if they've already run through the model, they're going to already have sort of adjusted the model exactly for those houses, so you're going to get really good scores from that, when it maybe shouldn't be. All right, so this is where the coding comes in. So we're going to have to go back, and what we're going to do is we're going to take our initial set of data that we get. We have this huge set of 149,000 houses, I think. We need to start by just breaking that into 2 classes. One for training, a big chunk for training, and a smaller chunk for validating. So we're going to hold back some of the houses we would have fed through our model, and we're going to hold them back in a set over here so that we can use it for actual coding or validation later. To do that, we're going to use another tool from the sklearn. This time is from the model selection part of sklearn. So from sklearn.model selection, we're going to import a function or a group of functions called train test split. And this is what's going to give us the ability to take our data and quickly split it up into different stuff. The actual code for the splitting happens here. You don't need to know the full details of this, but Python is a really cool language. This train x, val x, train y, val y is us creating 4 different variables. Remember, Python doesn't need var to announce that it's creating a variable. You can just create them just like this. And when you put commas in here, it knows to create those 4 variables. Now, these need to be in this order. And then on the right-hand side of the equal sign here, we're going to use the train test split. That's a function inside this import we did up here. So that's where this is coming from. It's going to do a bunch of stuff. The way this works is this first thing is your features still. So this code would come in right, let me come back up here. It would come in right here. So right before this decision tree regressor stuff. This code would come in right here to then split the data. So it's going to split the X. You're going to tell it what the features are, what the price is, and you're going to give it a random state. The only reason to do this random state thing again is so that it just does it the same way each time. If you don't include this third-party random state, every time you rerun the code, it's going to split the training and the validation slightly differently. For our purposes, we want to be able to rerun it and get the exact same results every time. If you don't choose a random state here, you're going to get a slightly different set of numbers every time. All right, so it's going to do a train test split X, Y. It's going to put the training, the ones it selects for the training data, all those X's in this first variable. It's going to then take the rest of the X's that it didn't use for training and put them in something called the validation list. And then it's going to go over to the Y. It's going to choose a bunch of the Y ones to put in the training Y one, and then the validation Y ones. And it's going to make them so that the train X and train Y, all of those lists are in order. So the same house and train X matches up with the train Y. It's going to keep everything sort of balanced in both of them. So now we've got 4 lists of data out here. We've got this one with all of our X data, the house price or the house square footage, year built, longitude, latitude, all that stuff is in here. And that's most of the houses are in that one. Some of the houses are in the val X one. And then the train Y one is going to be all of the prices that match up with these train X ones, and then the val Y's, all the prices for the houses in the val X one. Okay, so crazy right now, but we've got 4 lists: a train X, a train Y, a val X, and a val Y. All right, now we're going to pull in our model, and we're going to create a decision tree regressor, just an empty one, and we're going to store it into the Melbourne model, and then we're going to fit it. But we're going to use, instead of just all the whole X and Y, we're just going to use that training set of X and train Y, and we're going to train it with that data. And so it's going to go through and do all of its twisting and adjusting to the decision tree regressor model until it gets something that's predicting really well for the X's, the train X data, and the train Y data. All right. Now we're going to run our predictions, and we're going to say, our val predictions, we're going to rename our prediction variable here and call it a val predictions. And we're going to say the Melbourne model, so take the model we just fit using the training data. And now instead of predicting with the training data, the data it's already seen, we're going to use that validation data that it hasn't seen yet. So our model has never seen the houses in the val X data frame. We're going to send those houses in. It's going to save all of the predicted prices for those houses into this thing, val predictions. Now, when we run the mean absolute error, we're going to compare the val Y, which is the actual values of those houses in the validation set, compare them against the predictions that our model gave for that Y. When we do that, we get an error of $265,000. So this is unusably large amount of error. If I told you, hey, I could predict the value of your house and it'll be plus or minus $265,000 from its actual value, you'd be like, no, thank you. I don't need that kind of a guess. You want something much better than that. And that's a huge difference. Remember, when we used all of our data to do the training with, and then we used all that data to do the validation with, we thought our model only had $434 of error in it. So we thought we had a fantastic model. That would be amazing if I told you, hey, I can predict the value of your house to $434. You'd be like, yeah, that sounds pretty good. If you can guarantee that, I'd be happy about that. But in reality, what I was doing is just reusing the numbers that the model had already seen. By using numbers the model hadn't seen, I see, oh, my model has lots of problems. So over the next couple lessons, we're going to be looking at how do we take a model that has lots of error in it, and how do we take that and make it a better model? And we'll do that by choosing different features, by choosing different trees, the model trees that we're using, decision trees that we're using, and just by playing around with some of those features. Awesome. Good job today.